I'm probably going to do a review here because they're kind of all the, like I said, we all ended in a different spot here. But lesson 12, again, we have this part here. We have covalent bonds that exist between specific pairs of atoms. It's possible to predict these three-dimensional shapes. There's going to be 6 of them. We started one yesterday based on their little Lewis structures. We talked about VSEPR, valence shell electron pair repulsion theory, where electrons pair up and want to repel each other. The theory is based on, like I said, and repulsion is maximized, yes? So the repulsion has to be maximized. I think I wrote that down there yesterday. Basically, lone pairs, if you have lone pairs on these molecules on the central atom, we'll talk about that again, but if you have lone pairs on the central atom, they repel the most. We might say repel, they mean push away from themselves the most. Lone pairs always repel the most, okay? And then if you had bonding pairs, they're kind of just bonding pairs. They repel the least kind of thing. They still repel, but there's kind of an order that goes here. And please remind me when we get to the last 3 examples, I'll show you the difference between those 3 and why that happens, okay? This was a little confusing. We have this AX and E thing. I like to call it axe because it sounds cool. And it spells axe. I play guitar, just saying. I have an axe. I have 2 axes. One's acoustic. And I operate a forklift while playing the guitar. That's a lie. Not safe, people. Linear was the first one. I think we got this far, yes? Yeah? Linear is the first one. Am I recording this? I hope so. Oh, yeah, there we are. Okay, good. I'm a little bit off today. I don't know what's going on. We'll see. I shouldn't record this because no one cares. But, linear, AX2. We have a bond angle 180, and it usually it has a 2 double bonds or a single and a triple. Okay, and I think the first that we got to CO2, did we not? I think as an example, yes? Is that correct? Okay, so I said CO2 is an example of this. And again, you might say, oh, how do you know CO2 is an example? Well, because we're starting the examples, yes? So I know that obviously this would be an example of this that would fit into linear. We'd connect these, connect these. I said, hey, maybe these 2 here can kind of form a bond, and these 2 here could form a bond, and we'd end up with another double bond there. So 2 double bonds like that, okay? And then yesterday I made it all pretty. We kind of try and get those pairs of electrons away from each other. And I'm not sure how I'm going to do this yet. I might have to just demonstrate this because we can't be touching a bunch of Lego stuff. So I probably will just have to do this, unfortunately. But you're going to see that this is the only option really. Once you get to this stage here, this is the only way that they can kind of combine together. Okay. We call this the central atom, so that's an A. I don't care how many bonds it has, to be honest. Like that has nothing to do with anything. I have an atom that's bonded to the central atom. I have an atom that's bonded to the central atom. So then I know that this is AX2. All right. There's no lone pairs on the central atom. Look right here. And this is important because people always want to tell me there's lone pairs. There is, but there's none on the central atom. And all I care about is what's around the central atom. That's all I care about. So if you look here on this C right here, there is no lone pairs. So this is just AX2, okay? And once you know it's AX2 now, okay, this is kind of the steps you're going to go through for homework today. You'd be like, oh, okay, this is AX2. And then you just write down the other stuff that goes with it. Well, that's linear. It's 180-degree bond angle, okay? Yeah, and that's all we're going to do for today, I guess. Okay, good. Another example of AX2, and again, we wouldn't know this per se yet, but would be this one here. Oh, by the way, going back to here for a second real quick. Look, it doesn't matter what atoms are bonded to the central atom either. So, for example, let's say I didn't do carbon dioxide. Let's say I did COS. So I ended up with a sulfur there. It's the exact same, okay? I don't care that the atoms are different. For this part here, it's still AX2, it's still linear, it's still 180. It does change something else though for us, which we'll talk about not today, all right? That's probably a tomorrow thing somewhere there. So that doesn't really affect us for today, all right? There's just AX2 linear, that's still important, 180. Tomorrow, we'll kind of adapt what that really means for us, okay, in that case. All right, HCN, let's copy that one down. This will be new for you. again, if I was going to draw this one, I'd make maybe a list of neutral atoms, right? These are all non-metals, so it's a H, C, and N. It just happens that probably I would start with C in the middle, yes, obviously, just like we did before. Or, again, if you want to add up electrons and then put them in the right spots, go ahead, do that. That still works, okay? C would go here, probably H I'd put here. I'd connect those two because H can only form one bond. And then I got N here. And again, connect there. And then I was like, oh, well, I could probably connect those two right there, boom. And then I could probably connect these two here and get, like it says in the notes there, basically a triple bond, okay, right there. All right. And again, you might have to, you know, take your time and draw that out a few times or whatever. Probably the best diagram, again, would be if we're trying to get stuff away from each other, probably put those lone pair there probably. And again, once we get to the model thing, you'll see that that's where they have to go. There's not really any other options. Again, you know, case in point, this is A, that's my central atom, X, X, okay? And that's AX2, linear. Okay, bond angle. The bond angle is between bonds, so that's that part there. That's the bond angle, okay? And now when we get to the other ones, well, we'll kind of talk about that, but that's 180, it's linear, AX2, okay? And again, you can see that those atoms are different. On the ends, it doesn't matter, okay? That's still linear. Good? Okay? So the first step is always you're gonna have to draw it. So you gotta be able to draw these diagrams. Then you're gonna match it up to the appropriate formula. Then you know it's linear 180 because you study. All right? Good? Questions? Are we done or not yet? Good? Yes? Okay. So there's kind of some, you know, fancier diagrams or whatever, CO2 and HCN. We're going to copy this. Do we? I don't think we really need to. I don't think we need to copy this. Yeah, it's fine. I'll let you guys copy here. Okay, their second shape, or second structure that we're going to talk about is something called trigonal planar. Trigonal means what? When you think trigonal, you think, yeah, trigonometry, no. 3, yes? Okay, so there's going to be probably 3 things. And planar, what does plane mean? What is a plane? Like not this kind, no. Everyone's no. Anyway, we can't even, or I guess we can try, anyway, it doesn't matter. It's on a flat surface, yes? Flat surface. So basically what they're saying is all these atoms are going to line up kind of on a flat surface. So they're going to, you know, for example, they'd be on this board, for example, okay? There's 2 different possible, the symbol's AX3, trigonal planar. Notice 3 things around the central atom, yes, trigonal planar. There's different bond angles for these. So there's one that does 120, 120, 120. Okay, we'll show you that. And there's one that does 121, 121, and 118. And you're going to see which one is which, basically, once I draw these out for you here. Okay, some examples of this. Now, we'll start with this one. This is a pretty common one, CH2O. Okay. Again, you probably want to start with, and I would probably have to give you this formula because I don't know how to name this otherwise, right? When we talk about non-metals, we only know 2, like nitrogen trifluoride, H2O kind of thing, right? So this is CH2O. So I'd probably start with a C. We're going to do some neutral atoms, H, and I need an H, and I need an O. Okay? And so start with some neutral atoms. The drawing, okay, I'm going to tell you right now, the drawing is the most important part. Because if you mess up the drawing, we mess up the formula, the shape, and the bond angle, and then this and this and this down the road, okay? So we're going to start with C in the middle. And again, if you want to count up electrons, if you want me to do that, I can do that. We need to put an O1 somewhere. You pick. This is my central atom, so I'm going to put an O up, maybe up here, like that-ish, maybe. And then I'm going to put 2 H's on, and maybe I'd put them, I don't know, here, It doesn't really matter. I'll even stick one right there for just change it up. I was going to put it somewhere else, but that's okay. I'll put it there. Okay. And again, you can start connecting some electrons. Remember, hydrogen only forms one bond, so there you go. There you go there, right? There, you got to connect the outside atom to the inside atom at some point. And oh, lo and behold, look, dot, dot, right? We can make a double bond there, yes? So I'm going to actually do that right here. Double bond to the O. Probably put that on a little bit of an angle there. And then put an H out coming out this way, and maybe an H coming out this way, okay? Notice how A, okay, is in the middle there. And then all my atoms that are bonded to it are kind of spread out. Repulsion is maximized, yes? Now, let me ask you this. Take a look at this molecule. I'm going to tell you this. Molecules like to, you know, in some cases, they like to be symmetrical, right? Think about back to our last example, CO2. Look the same kind on both sides, yes? So do you think that this is going to be the same all the way around? In other words, if we looked at bond angles here, do you think this bond angle and this bond angle and this bond angle are going to be all the same? What do you think? If you had to guess. Pairs of electrons pair up and repel each other. And the more pairs you have, the more repulsion you actually have, yes? So do you think they're going to be the same all the way around? Probably not, okay? So this is our 121. See, right here, we have more pairs of electrons there, yes? So even though they've paired up, they're pushing a little bit more than just these other regular old, this is just 2 electrons here and 2 electrons. Technically, I have 4 altogether there, yes? So they push a little bit more. And if they push a little bit more away from them, this would be instead of 120, 121, 121. And by default, that has to shrink to 118 in that case. So that would be an example of the 121, 121, 118 example, okay? Does that make sense? This is obviously, like I said before, this would be, and I kind of skipped this part, AX, X, X, yes? So AX3 is what I would call this. And then as soon as I put down AX3, I say it's trigonal planar, which of course we know that because we're doing that under this example. But when you're doing homework today, that's what you're going to do. Trigonal planar. And then because this one has a double bond there and a single, 121, 121, 118. Okay? So those push a little bit more. All right? And of course, we know that in this case, okay, it says that they're all on a plane. So that means they have to be 360. They have to add up to 360. If they're going to add up to 360, you know, our options are 120, 120, and 120. That adds up to 360. Get a calculator. Or 121, 121, and 118 in this case. Okay. So this is probably, I would say, more common of a situation. So this is probably the AX3 molecules that you get for the most part. However, just to mess with you, I like to do this one. I'm just going to do, let's just do boron trihydride. Okay. Now, when you go to do boron trihydride, actually, I probably should have picked a different one because that would have given you an option here. Boron has 3 valence electrons. We haven't drawn a lot of boron molecules yet. There's a reason. And if I'm going to do 3 hydrogens, I'd probably put one here, and one here, and one here. Okay? And some of you are thinking, well, that's pretty easy. Look, boom, boom, boom. Yes? Okay? So the next question I'd say is that a good drawing? Yes or no? Some people are shaking their heads. Some people are like, that worked out really well. Some people are thinking it's not really spread out very well. So what if that's because I know that's what you're thinking, maybe some of you. What if I did this? Does that make it better? Is that better for you? Okay. No? Yeah, some people are like, yeah, that's better. How many people are still not happy about it? Why? Well, yeah, boron technically only has 6 electrons, right, is what you'd say. And so therefore we know it doesn't follow the octet thingy, right? So how are you going to fix it? And the answer is, well, you're going to hate me. You don't. Yeah. Boron is one of the few that are allowed to get away with 6. Okay, it's an exception to the rule. So there's always going to be exceptions to the rule. Here's the case. Okay. We're not going to get into why. You can look it up on the interweb if you want. But this actually is okay. This is 120, and this is 120, and this is 120. This is the one that's perfectly symmetrical. Okay, this would go like boron trihydride, boron trifluoride, boron trichloride. Okay, there's not many options here really, because and I usually give you these ones because we don't know this yet, but it's going to apply tomorrow. Okay, that's why we give you these ones. So again, this would be A, X, X, X. Okay, or AX3, trigonal planar. This one, of course, you can see it's perfectly symmetrical. It's 120, 120, 120. So that's what you're going to have to memorize, that one. The boron ones, okay, boron's allowed to have 6 around it. We do not have to make it an octet. Don't make it an octet because it'll screw stuff up, actually. Okay, so boron is the exception. Hydrogen is an exception because we only need 2, of course. Okay, I don't know. I don't remember if there's any other exceptions off the top of my head. I was trying to think. I think there's another one, but I don't know what it is. So obviously it's not important for us. Okay, anyway. Okay, good. So that's AX3. Now, next one we're going to look at. So there's some examples there. BF COCl2 would be an example as well. Okay, we draw that. They kind of look like that. The next one we're going to talk about is trigonal planar bent. Okay. I'll let you copy that there. So trigonal planar, and we have to call it this entire thing because we can't just call it trigonal planar because that was the last one. We can't call it just bent because that's another molecule that's probably coming up that's more famously bent. So this is trigonal planar bent. You're going to have to write that all out, trigonal planar bent. You know, it says in brackets, but whatever, doesn't matter. Trigonal planar bent. This one's AX2E. Now, here's our first example of an E here. So, and the bond angle it says is 120. Our example is SO2. Now, just be patient for a second here, because this is going to be a little review for us. That's why I really wasn't doing anything else. But if I just relax for a sec, I guess if you wanted to do this part, you could. But again, up to you. But I wouldn't go any farther than that if you're going to do anything. So obviously we start with some neutral atoms. You'd say, well, which one goes in that? Which one has the best bonding capacity? And you'd say, well, all of them. Yes, they're all 2, right? Bonding capacity to 2. Let's not forget those terms. Which one are you going to put in the middle? Probably most of us would pick S. You don't have to, but probably S. Okay. But here comes the issue. Okay. If I do decide to do it this way, and sometimes you're going to see this happen. Now I'm telling you a lot of stuff here, so I get that, but you're going to have to maybe write down a few things. You might say, okay, well, I'm going to do this, and obviously you'd match up the unpaired electrons because you want to make this molecule, right? But here becomes the issue. That. Now, what do I do with this? And the answer is you cannot connect these 2 together, okay? Because look, first of all, if I connect, don't do this. If I did, and that's you have to pay attention here because otherwise somebody's going to do this and it's going to be wrong. If I did do this, which one's the central atom now? The answer is all of them, right? Or none of them, really. Because you might say, well, S is, but no, because then this could be in the middle and I could connect that to that, or that one's in the middle and I could. That's the first thing. The second thing is there is no such structure as this. We do not make circles or rings, we call them, okay? Now you can in Chem 30, but you do them with carbons, okay? So carbon to carbon to carbon to carbon to carbon to carbon. Yes, they can make long lines. We're going to look at those this year. They can also make circles. or like rings, pentagons, hexagons, octagons. We call those like octane, nonane, decane, pentane, propane, hexane. Oh no, sorry, that's not even true. What am I talking about? Those are long chains. We call those cyclos, cyclohexane, cyclopropane, cyclobutane, cyclo whatever, etc. And then you can throw double bonds in those too. Carbons are really good at making ring structures, and they're very good at making long chains. Okay, so carbon to carbon to carbon, yes. This, nuh-uh. Okay, not an option. So you might say, well, how am I going to fix this then? How am I going to fix this? I have a feeling this is not going to work out. I have a feeling that this is already off. We're going to have to pause pretty soon. How are you going to fix this? And the answer is you're going to not do it this way. You're going to be like, okay, I'm stuck. Maybe I should add up some electrons instead. Okay, so let's take a look at that. Let's see how this goes here. So 6, 6, and 6. Yes, you're going to add up all the valence electrons. That is, oh, yeah, I'm behind here. I'm going to try and struggle through this. 18 electrons, yes? Okay, 6, 6, and 6. You're going to add up all electrons. You're going to draw a skeleton structure. So S, O, no. And we're back. Okay. So I would draw, I'd add up the electrons. I'd put S in the middle, put an O here, an O here, because that's going to be my central atom. I'm going to put in 1, 2, 3, 4. Okay, good review here, right? This was your quiz on polyatomic stuff. So 4. Then I go to the outside atoms first. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I've used up 16 electrons so far, and then I'm allowed to go to the central atom, 17, 18, right? You look at the oxygens and you say, okay, well, the oxygens are good. They have 8. Oxygen has 8. Sulfur good? No. So I'm going to have to fix that somehow. I'm going to have to move a pair of electrons in. So I'm going to take a pair of electrons and move it in. I'm not going to put brackets and charges because I am just using this to get sulfur dioxide. That's it. Okay, so I'm going to move a pair of electrons in, and I'm going to get something that looks like this before I get too crazy here. Okay, good so far? Questions before we move on here? Anyone? So I move that pair in to make sure that sulfur has 8, because sulfur obviously needs 8. It's not boron or hydrogen. Okay, now I kind of need to draw this a little bit better, because this is probably not, like if I looked at this and said, what's the shape? I'd be like, I don't know, okay? So I'd probably say, well, you know what? Let's maybe look at this and say, okay, here's my central atom, S. Lone pair, right there. I have a single bond to O. That's gonna come down here. A lone pair takes up a spot, okay? Lone pairs take up a spot on the central atom. So when we do 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock kind of stuff, that's one of those positions. And then I want to get stuff away from that, right? So if that's going to take up a position, then I'm going to have to do a double bond here, right? That's that part right there, double bond. I probably shouldn't do that. And then I'm going to have an O here, double bond O, like so. Okay? Questions on that, anyone? Yes, no? This, I will tell you, is the least common one that we will draw. This is not very common, but I will give it to you because that's the kind of guy I am. Yes? No, it doesn't. In fact, to be honest, this isn't probably even that accurate. It probably flips back and forth between the two, and there's probably not even, there's a chance there's not even a double bond in here, to be honest. They're resonance structures, and they just kind of, if you looked at those bond lengths, they're probably the same because they flip back and forth so fast. So what we have here is A, okay? E, there's my first E, lone pair on the central atom, okay? I can't say that enough. Then there's an atom that's bonded to it and an atom that's bonded to it, okay? Again, I don't care about double or triple or whatever bond. I just want to know what's around the central atom. Now, the bond angle here, and of course, then you'd say, okay, well, this is AX2E, yes? And that's where we get that formula AX2E, trigonal planar bent. So that's what you'd say, trigonal planar bent. And the bond angle is 120. The only bond angle here is right here, 120 degrees. Okay, you might say, well, geez, that doesn't really, there's a double bond and a single bond. Yeah, but you have to remember that there's no other bonds here. Those are the only two bonds we have. This, look, and again, this sounds stupid, but let's be honest, like, I know this is, you might say this is silly for you to say that, but a bond angle has to be between bonds, okay? This right here, I don't know what that is. It's not a bond angle, okay? Because it's between lone pairs in a bond, and that doesn't, that's nothing, okay? And same thing here. That's, I don't know what that is. Some people want to say it's 120. I have no idea because there's no bond there. You can't say that, all right? I don't know what the, there is no angle there because it's not between bonds, okay? So it has to be between bonds. So that's the only angle we have. We go with 120 in this case. That's what they say, all right? Good. The next three are you've seen before. So nothing new here. We're just going to attach some names to them, okay? Here we go. We're just going to copy to there. Just to actually right up to here. That's probably fine. Up to that point right there. I'll let you copy. I'll get out of your way. Does anyone know an example of tetrahedral already? We've drawn, you know, we've drawn quite a few already, but what has four things around the central atom? Give me an example. Yeah, absolutely. Carbon tetrahydride, right? Carbon tetrafluoride, carbon, you know, really good at having four things around it, isn't it? So carbon tetrahydride, carbon tetrafluoride, carbon tetrachloride, carbon tetra whatever, you know, those are really good. The bond angle here is 109.5, and we have to remember that these are three-dimensional. So an example here would be, yeah, you know, CH4. Well, carbon has that, right? And I'm just going to jump right to it. H, right? So boom, 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 boom. That's tetrahedral. AX4, right? A, X, 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 X. AX4, tetrahedral. The bond angle here, this is the only tricky part about this. Only tricky part. I mean, we've drawn that. You guys are awesome at that. I know that. That bond angle, okay, looks like 90. People just heard me say 90. It's not 90, okay? It is 109.5. It's 109.5. No matter where you go here, these are, you know, it's pretty much all symmetrical, right? So all those bond angles are 109.5. And of course, you'd say, Mr. Bachek, 109.5 times 4 is not 360. It's not supposed to be 360, right? Because these are what? Huh? These molecules, AX4 is what? We just took the notes on it. I can't hear you. Speak up. Three-dimensional. So they're not going to add up to 360, all right? They look a little something like this here. So if you actually, I mean, if you want to draw this kind of stuff here, like this whole, like that kind of thing, and that, you know, and that, and then that kind of thing, basically implying that there's different, some are coming out and some are going in and some are going up and down and all this other stuff, that's fine. You can. I don't, because I can't draw. And two, we usually don't, okay? But I know this looks, you might say that doesn't look right to me, but you have to just trust me on this. When we do the molecule thing, you'll see we're not quite there yet when we play with the kits. Well, when I play with the kit, apparently, which sucks. But that's 109.5. You're going to see it's symmetrical. You can flip it any way you want, and it still lands exactly the same way it did before. Okay, just kind of like flip-flop. There's 3 on the bottom and 1 sticking up, and then if you flip it over, there's 3 on the bottom and 1 sticking up, and it just keeps going. Like they look exactly the same. Okay, it doesn't matter which way you turn it. So that's 109.5, that's 109.5, that's 109.5, that's 109.5. Okay, it's kind of hard to show you on the board because it's 2-dimensional. Now we're talking 3-dimensional stuff. Okay, And we'll get to that part, I promise. All right. So CH4, CF4, CCl4, blah, 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 AX4, tetrahedral 109.5. Good. The next one we're going to talk about is this one. Okay. I'll let you copy again here. Almost done. Okay. So again, yes, it's tetrahedral because how many things are around the central atom? Look. Well, there's 3 atoms, it looks like, yes. 3 atoms and a lone pair. So there's your 4 things around the central atom, right? That's why it still belongs to this tetrahedral family. But we probably, when I talk about this shape, we don't call it tetrahedral trigonal pyramidal. You can. I just call it trigonal pyramidal because there's only one. Okay, trigonal pyramidal. Don't get that confused with trigonal planar. Planar means it's all in the same thing. That's AX3. This is AX3E. There's 4 things, trigonal pyramidal. Okay. Bond angle is 107.3. We'll talk about that in a second. And NH3 is a pretty good example here. NH3 looks a little something like this. I'd start with N there, for example, H, boom, boom, and boom. Yes, NH3. So something like that. Okay. And then again, I'd have what? A, E, X, X, and X. Sometimes what you'll see is we kind of draw the X's a little bit, not straight across from each other like that. So you might see this a little bit. It doesn't really matter a whole lot. You might see X, X, and kind of X like that. Okay. We'll talk about that in a second. But this is AX3E. Then you're like, okay, it's trigonal pyramidal. Trigonal pyramidal has a bond angle of now 107.3. So this part here has actually changed. First of all, it is 3-dimensional. Second, okay, it's not the same as CH4. CH4 was 109.5 AX4. This is now 107.3. Do you have to know these bond angles? The answer is yes. Okay, so that's 107.3. You're going to have some studying to do. It's fine. Okay, we'll come back to that and we'll talk about that in a second. Yep. Yep. Last one. Okay, last one is tetrahedral bent. Let me. Okay, so tetrahedral bent. Now this one we will call it tetrahedral bent, but when we say a bent molecule, we usually refer to this one. Remember how there was trigonal planar bent? That's a pretty specific one. That's not very common. This one's very common. So if I say it's a bent molecule, we're probably talking about this one. I like the word tetrahedral bent, but sometimes it's just referred to as bent. Okay. So if you're going to leave off a name part there, you could, because it has 4 things around the central atom. So bent. This is pretty common. It's AX2E2, R2D2, C3PO, Chewbacca. That's my Chewbacca. Just in. You guys know Chewbacca, right? It's pretty good. All right. They asked me to do the thing for that, but it's Star Wars is over now. So tetrahedral bent, AX2E2, R2D2, C3, no, 104.5, and you know the most common example we have here is good old fashioned H to the 2 to the yo. That's rapper stuff. Right? H2O. Okay, H2S would be another one. But this here, of course, would form water. It's probably our most common example of a tetrahedral bent. Again, you know, that there's nothing wrong with that diagram. I probably wouldn't fix it a whole lot. You know, if you wanted, sometimes quite often you'll see it kind of like this and like this. Okay, whatever, it doesn't matter. But, you know, again, we have A. This is the most important part. E, E, and then X and X, right? That's how we get the AX2E2. AX2E2. Okay. This bond angle has again changed. There's only one bond here, by the way. It's right there. So this bond angle now becomes 104.5. Okay. Good. and that would be a pretty common example. This one's fairly common, I would say. Obviously water, but there's other compounds that do this as well. You'll notice there's only 6 shapes. We're done them all now, but there's only 6 shapes because really, what do the shapes depend on? What does it ultimately come down to, do you think? It's all about what? Anyone? It's all about what? Yeah. Okay, that's a very complex answer. I know what you're saying. Yes, probably true. You're right, but it basically comes down to, very simply put, you're right. I get what you're saying. You're right. But it comes down to A, doesn't it? And there's only so many A's you can have, yes? When we're talking about nonmetals. In other words, there's only so many central atoms you're going to have. And really what's around that central atom, right? So when you're talking about carbon, you know, carbon, okay, is either going to form 4 bonds, maybe 3, I guess. But, you know, that right away tells you 2 of the shapes right there, yes? It's either going to be tetrahedral or maybe one of the trigonal planar ones or something, right? And if you put O in the middle, well, geez, you know, you got these 2 lone pairs here. There's only 2 things that are going to connect to it. So right away, AX2E2 is probably a good bet on that, right? Look, O is there. Where's S? Right below it. Well, that's going to look probably similar if we put S in the middle, and so is SE, right? So there's only 6 shapes because really it just depends on that central atom, what's going in the middle, and how many things are bonded to it. That's all it depends on, you know. There's only so many ways to make pancakes, you know. I don't know. I just came up with that. Baja salads. Baja. That's funny. Okay. Now, last thing, real quick here. I would maybe actually copy this just somewhere. Just put that one down. And that one. And we'll do this one again here. Okay. Now, again, we talked a little bit about, at the very beginning of this lesson, we talked a little bit about this, okay? Now, you notice that's a bonding pair, bonding pair, bonding pair, bonding pair. So they're going to try and split up perfectly evenly from each other, right? There's not going to be any imbalance here. So they try to get as far apart as possible from each other so the repulsion is maximized. That's why we get 109.5, 109.5, 109.5, 109.5, yes? Okay. However, in the notes we took today, this one has a lone pair. And because this has a lone, why don't these, remember, these are all tetrahedral molecules, yes? They all have 4 things around them, technically. Tetrahedral, trigonal pyramidal, and tetrahedral bent. So they all have 4 things, but the difference is the number of lone pairs we have, yes? That's really what it comes down to. Lone pairs repel more. That was the first part of the notes. Lone pairs push the most away from themselves. So that's why we get a little push here and a little bit more push here. And so when we draw this, you know, you don't have to do this, but I'm just saying that's why sometimes you'll see that kind of thing there, because those lone pairs kind of, just to exaggerate, push a little bit more. Well, if they push more, if they're pushing on this and this, as a result, no matter if it's 2-dimensional or 3-dimensional, that has to shrink a little bit because we don't have as much space between them now. We can't spread them out to 109. Now they only spread out to 107.3. Okay, and same with that part there. And again, there's only 2 bond angles in that one. Okay, but that's why we get a different bond angle, because of those lone pairs. And then if we look at water, well, geez, water, you know, quite often we'll draw it like this kind of thing, to kind of show you that, hey, we got 2 sets of lone pairs here. 2 sets of lone pairs repel even more than a bonding pair, of course. So they're really pushing here and here. And as a result, because those lone pairs are pushing so much, that shrinks that way down to 104.5, okay? But it's all based on the fact that lone pairs repel more, okay? that really helps us out with water, actually. We know that water is what kind of molecule? Do you remember? You know this. Cohesion, adhesion, all that stuff. Water is very polar. Yeah, sure. Polar, very polar, right? And the reason it's very polar is because it gets a very, very negative end and a very, very positive, and those lone pairs actually help that happen, okay? They help push those other bonds away so that they're not quite as symmetrical anymore. So we get this very negative end and very positive end to water, right? Which we're going to talk about. That's tomorrow. That's what we're going to talk about. Which of these molecules are polar? Which ones are non-polar? Okay, and then we're going to talk about which force does that imply. Okay, all right, moving on. There we go. There's water H2S. We're not going to copy that. This is in your notes, I think. Well, it should be. I don't really. I think beneficial. Yes. I think you should make your own study sheet for this. To be honest, I would think I would, put down AX2, put down linear 180, blah blah blah, and we'll add on to it as we go here. But at this point, and it says all bonding pairs and all that stuff, I think as long as we know the formulas, the names, and the bond angles for today, that's kind of what we're at. But we'll add on to that eventually. Okay, so here's our homework. But before we get to this, here's what we're going to do for these. I'll scooch it up here. Again, this is in Google Classroom here. There's more down there, so don't bother taking a picture yet. But here's what we're going to do for each one of these. Very first step, you have to, of course, draw it, okay? So step one, we're going to draw the molecule, okay? 2, and in notes they call it the AX symbol or the AX2 or AX3, whatever. It doesn't necessarily have to have E, right? We know that. But the AX symbol or formula, if you want to call it, I call it the formula, but it says in the notes symbol, okay? That, and then we're going to do the name of the shape. So trigonal pyramidal, trigonal planar, yada, yada, yada. 4, we're going to do bond angle, okay? So I want those 4 things for each one of these questions. Bond angle, and I'll scooch it up here right away once we get that copied there. Maybe I can do that now. Okay, now there's a couple at the bottom here as well. So just before we get too crazy here, so we're going to draw the molecule, right? Do the symbol thing, write down the name of the shape, do the bond angle. There may be a chance, and I don't know if it happens here right now, maybe it's farther down. There may be a chance that you get 2 central atoms, okay? If you get 2 central atoms, like for example, a carbon and a carbon in the middle, right? I mean, how are you going to decide? The answer is you're not. You're going to pretend, okay, what would be the shape around this carbon? If I used the things around this carbon, what shape do I have? And if I had this carbon here, what's the shape here? Okay, so you'd break it up into sections basically, all right? And they might overlap. So, you might be, for example, let me just show you real quick here. If I said C, I don't know, let's just do this one. Just for fun, So this is how it works, all right? If you have more, now I'm not going to give you this on the quiz or the test, or sorry, not the quiz. The test might have something like this, but it probably wouldn't be. It might say, what's the shape around the carbon on the left-hand side, or whatever kind of thing. But this is what you'd do. You'd say, okay, well, which of these is the central atom? You'd say, I don't know, because they're both the central atom. Yes, I mean they're both that. So I'd say, okay, what's the shape around this carbon here? If I looked at this carbon, what do I have around it? Well, this would be what? Let me do it in this color here. A, X, 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 and I would call that X as well, because that's an atom bonded to the central one, right? Does that sound right? So that'd be AX4 tetrahedral, yes? Okay. Does that make sense? So I'm just looking at this. What do I have around this A here? What do I have around this C? I have X, 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 X. So I call it AX4 tetrahedral. And then if I went to this C here, I'd say, okay, what's the what's around that central atom? Well, I'd say this is X, 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 and this is X now, okay? So I just look at that C, basically pretend that this doesn't exist here, okay? And say, well, that's A, X, 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 X. That's AX4. That's also tetrahedral, okay? So I'd say, well, this side's tetrahedral, that side's tetrahedral, okay? So you can break it up into sections if you have to, okay? I don't know if, I just looked here real quick. I don't think that's an issue for these ones anyway, but yeah, I don't know. And then there's a couple at the bottom. We can still do those because they're still going to form a shape as well, all right? So NH4 1+ and a little carbonate there just for a little review skis, okay? Other than that, I think it's okay. We're going to get more practice tomorrow. We're going to do the same thing tomorrow. We're going to just add on to it a little bit. Don't want to miss tomorrow, if possible. And if you have to, that's fine. All right, I'll YouTube it. Yep, yep. I'm going to start.